Good morning, everybody, and welcome to Particle Classroom Series number 5, Sampling and Dispersion. This morning we have Dr. Jeff Bodycomb, who is going to be the presenter. Please take over, Jeff.
Okay, well, thank you very much. Welcome, everybody, to a discussion about sampling and dispersion. I'm with HORIBA Instruments, and we're the particle characterization group, so we get very interested in this topic. Okay, so I guess the first thing I should mention, or as an introduction, is particle analysis workflow. And there's a NIST recommended practice guide on particle size characterization, published back in 2001. And it goes through a lot of good topics, and one of them is this workflow. And about half of the steps are really getting the sample ready to go into the analyzer. So it's kind of sampling through specimen preparation. And then really instrument calibration through reporting is what happens after you have a sample. So half of your effort comes into getting the right sample and in the right shape, and I should say presenting it to the analyzer properly. A significant fraction of our application questions come down, at least in part, to these questions of sampling and sample preparation. And so we like to pay attention. We like to ensure other people understand how to do it, because if you make a good sample, your analyzer will naturally perform better. Or phrased differently, we only analyze what you put in the analyzer. So if there's something else that's never made it in, we can't tell you about it. So kind of as an outline is you'll have a sample from bulk. You might break that sample down into a smaller amount of material. You might do some sort of dispersion with a liquid or with air pressure and ultrasound. Sometimes you might split the sample further and then finally perform a measurement. Now, your measurement error sources kind of depend on particle size. Generally, if you have small particles, the sample extraction errors are not that significant in general, but your sample preparation errors and really that become the big headache. And that comes down to the larger relative surface area of small particles, which means they like to clump together more. Larger particles tend to have more issues with sample extraction. They can segregate more easily, though I'm not sure why. And generally, because the surface area is smaller with respect to volume, you have fewer sample preparation issues. Instrument error is that little dashed line at the bottom. Quite often, and I'm quite proud to comment that instrument error is not, it tends not to be a dominant issue in measurement. So if you do things like listen to me talk about method development, I'll say put a sample in and run it 6 times in a row and see how repeatable it is. And that's really where you're kind of getting at instrument error issues. And you see very tight repeatability. And then you clean the instrument, you put in a fresh sample, and then you see, oh, there's some more variation here. So let's start talking about sample extraction and good sampling practices. The old title of this was Learn to Love Your Riffler. So if you start with a process line where maybe you have a belt conveyor, you're feeding particles, and you want to take some of the material, you'll learn or notice that the particles will tend to segregate across the width of the belt for whatever reason. And so you don't want to just take off a little bit off the middle or a little bit off the edge. You really want to try to grab material from all across the belt kind of uniformly as it falls onto the next conveyor. And so you'll see duck bills that swing out, or you'll see a sampler that here is driven back and forth to pull off some material from process in an unbiased way. If you have materials in drums, you'll find yourself saying, well, gee, I can get to the top of the drum pretty easily. What about the bottom? And if you have material in a drum and in the truck and it vibrates, it will segregate. So you need to know what's on the bottom versus the top. For that, you would want to use a powder thief. This is a long pole with kind of doors in the bottom. You jam it to the bottom of the drum. You open the doors. That's step 2. The particles flow in. You close the doors. That's step 3. Step 4, you pull it out. Step 5, you take the sample out of the powder thief. You get that from an outfit like samplingsystems.com. So what you'll do is you might take off the star pattern at the top and in the middle and the bottom of a drum, and then mix that before you bring it to the lab for analysis. So depending on your large scale process, you're going to try different ways to get something representative. I was once talking to a geologist, and he said that he would have to dig holes at multiple spots on the beach in order to get a representative sample of the sand. I don't know the details, but kind of whatever application, there's some thought given to getting something representative. Here's another example of a powder thief where you have multiple doors up and down the length of the pole, and so you can pull particles into all the doors in one shot. So that's a little bit easier. So I mentioned kind of if you're taking all these samples from different points on a drum or a beach, or you have your duckbill on a process line, you're gonna have a fairly significant amount of sample. So you have a process stream with some enormous number of kilograms. You might walk into the lab with 1 or 2 kilos of material, or you might even divide it there and walk in the lab with a little bit less than a kilo. And then you're going to test between grams and milligrams. So not all the material that arrives to the lab is analyzed, and you have to subdivide the sample and ensure it's representative. So why am I so worried about all this? And kind of this figure on the right shows you it. If you have large and small particles mixed together and you shake them, you'll find the large ones tend to float to the top and the small particles tend to go downward. So if you take a container of sample and you walk around with it or have it on a truck, you have big ones on top, small ones on the bottom. So you could grab sample, which is kind of just hoping that the particle size distribution is narrow and there isn't too much of this segregation. And you just scoop out a little bit off the top and away you go. If you have narrow distributions, this works. It's pretty easy and it's pretty common. It's not always appropriate, even if it is common. What you should do when material comes in either a bottle or a bag is ensure it's well mixed before taking something out with a spatula. This is a big improvement over just putting the spatula in and taking off the top. When the powder is stored in the container, you want to make sure it's no more than about half full to 2/3, and then you'll start rolling the container about all of its axes. So you can see here, I roll this bottle around its long axis, and I tumble it around its short axis over and over again. And with the bag, you'll kind of do the same thing or knead it. And you'll see people who work with particles a lot, hand them a bag of sample, they start just kind of habitually rotating it in their hands to mix it up because they know that's what's coming next. Once the material is mixed up, then you pull the sample with a spatula. Okay, and that gets you a much more representative sample than if you simply dip the spatula in the top and hoped. Next up is coning and quartering. Here, you kind of take your container of material, you dump it out on a surface you hopefully is clean, and then you use a knife edge or whatever to split it into 4 sections. And then you take the 2 diagonal sections and throw them away, and you keep the other 2 diagonal sections. So this fellow here in the picture is going to take the section with his shovel, and then he's going to take the 1 diagonal from it, and he might decide to split it again in the same way. You just keep repeating this until you have a small enough material for analysis. So this can be carried out. You can use a tiny amount of material on a benchtop, or you can use a very large sample, say a drum of material and a shovel, as is shown here. And so it's quite flexible, and you don't need any extra equipment or specialized rifflers. So if you're kind of caught and you don't have anything else to work with, either because you have a drum of material you're really worried about, or because you want to make sure you have good repeatability, you would use coning and quartering. If you do get some tools, a chute riffler is your friend. So basically, a chute riffler, the particles come in, and then there are chutes that split it in one of 2 directions. And it splits it kind of randomly, so that first you start with 1 part of sample, this fellow pouring at the top, and then he has 2 bins at the bottom, and the particles should be pretty evenly separated. Now, a couple of things about chute rifflers. You do need to pick the right size. So if you pick one that's too small and your particles won't fit down the veins, well, then everything's stuck and it's not going to work. And if you pick a very large one, it tends not to work as well for fine particles or small amounts of material because it's hard to get this kind of random spreading of the material as you dump it into the riffler. Moving up in performance and in cleaning hassle is rotary riffling. This is really kind of the best way. You have a uniform feeder and you have a spinning table with a bunch of holes where the particles fall in, and you feed the particles at a very uniform rate and you spin at a uniform rate, and the particles just fall into each hopper kind of randomly separated. So things to remember: when you put particles on the hopper, you run through everything on the hopper until it clears out. because if the big ones are stuck in the back, you want to make sure they have their turn being split up between the small containers. Companies that make these, Fresh makes them Quantachrome, but as well. And here are some pictures of sample dividers. On the left and the middle are rotary type devices. The one on the far left divides it into 6, I think that was 8 representative samples. Another example is that you have kind of one small quantity and one large quantity. So you're really trying to just take 1/8 of this material for the middle. And the Chute Riffler is on the far right and divides it into 2 samples. So kind of which do you use depends on your needs. So if your size distribution is narrow, then it kind of doesn't matter that much because there isn't a lot of segregation and all the particles are close to the same size. And there are very few samples that are actually like that. Moving up in quality is going to be kind of taking scoops out of the bag. Then you would have the cone and quarter. Then you would use a Chute Riffler and a spinning Riffler. And so there's some studies and publications of the repeatability of various sampling techniques, kind of summarized in this slide here. So that's from Allen and Kahn in Chem Engineering, and then from Terrence Allen's powder sampling and particle size distribution. So the results will depend somewhat on your sample, and this becomes a judgment call which you choose. Because look, the spinning Riffler is great. Everybody says it has great repeatability. I absolutely agree. But you do have to clean 8 or 10 jars each time and set it up each time. And so it's a bit more of a hassle. Chute Riffler, in my opinion, is a nice compromise between real easy pour and go and fairly easy cleanup and good sample dividing. And if you do scoop sampling, that's the easiest. You don't need any extra equipment. And you got to remember that all these steps of cleaning or deciding what equipment to have is going to cost you money, and you may not need that much precision in your measurement. So just kind of something to keep in mind is that the Chute Riffler, I think, is a good sweet spot for most of the work we do. If we need real precision, we have a spinning Riffler. And I'm not above scoop sampling at a customer site just to get things going. Again, depends on your application and what your needs are. If you have a liquid sample, so if you have a liquid suspension, particularly with larger particles that tend to settle, you want to make sure that you have good vertical and horizontal motion for good mixing. Now, the great thing about liquid suspension is they are pretty easy to mix. You put in an impeller, and from the top, you aim it at a diagonal so you have good vertical and horizontal motion. Or I've even taken an eyedropper type of dropper and just squirt air in and out to kind of get everything stirred up before I draw material. Put a pipette in, go about 1/3 the way from the bottom, so you don't take off just the big stuff from the bottom or just the fine to the top. Sometimes you can also have a slurry and you mix the slurry and then pull off with a paste, and that's pretty easy. So nice thing about liquids, they're very easy to mix. Just pay attention, you're mixing in all directions. And remember, just because you mixed it before lunch doesn't mean it stayed mixed after lunch, because the larger particles will tend to settle. If you really wait a long time, you can even see some nanoparticles, like nanogold will separate if you give it many, many months in the lab. And that goes right back in suspension. So just mix right before you sample. Okay, so I mentioned nanoparticles, which is a good segue into what happens when I have small particles. Now, I'm a lot less worried about sample extraction. Generally, they're a bit easier to mix, and the size distributions tend to be a bit finer, a bit more narrow. But surface area gets very large, and so that leads to significant sample preparation errors, or significant sample preparation concerns is a better way to phrase that. So really, what you're worried about is if the particles stick together, your particle analyzer of whatever stripe will just pretend it's one big particle. And once again, instrument error tends to be fairly minor in this. So often we're making dispersions in liquid, and we need to choose a liquid. And we could argue about the choice of the word solvent, but really the point is pick something that will not dissolve your particles. So for example, if you are analyzing sugar, you do not want to do your analysis dispersed in water because the sugar will dissolve and you won't have anything left to look at. Conversely, if you're looking at, say, polystyrene pellets, then if you try to disperse it or I should say ground polystyrene because that's faster dissolution, and you have it in DMF or THF, you'll dissolve the polymer, you won't see anything. You then want to make sure that the particles are wetted, and you might need a dispersing aid to avoid reagglomeration, and finally some energy to break up agglomerates into your real particles. Now, this looks very much like formulation, and it is really kind of a formulation question. The great mercy is that when I make a formulation or a suspension, I only need to worry about it being stable for 30 minutes to an hour. So it's not like someone who's making a formulation for actual consumer work where you say, hey, I need this formulation stable for months. Nah, if it's stable for an hour, I can declare victory and move on. If I already have a suspension, most of my work has generally been done for me, and I simply need to dilute and add energy if needed to break up the loose agglomerates. So a few definitions. Well dispersed are particles that you can kind of see as distinct particles in an optical microscope. They don't show any tendency to cling together, and that's kind of a happy situation for particle analysis. Agglomerates are particles that appear in clumps, and they can be separated easily with moderate amounts of energy, such as ultrasonic baths or shaking or stirring or something like that. And quite often you do want to break those up because during use they will also be broken up into those well-dispersed particles. And finally, you have real aggregates, which are particles that are tightly bound and need a lot more energy. So now we're saying, is my aggregate what I want to measure, or is the primary particle what I want to measure? If the particles are very tightly bound, you might be adding so much energy that you break the particles before you separate them. So I mentioned particle wetting. Now I'm going to back up and tell you what I mean. If I put a drop of liquid onto a surface and it kind of beads up on top with a large contact angle, as shown on the right, then it means the liquid does not really want to adhere to the surface of the drop. As the contact angle gets smaller, which means I move to the bottom, the liquid spreads across the surface. So it means you have a low surface tension. It means the liquid is going to surround the particle and keep it away from its friend. You can measure contact angle. There are instruments available. So the reason I worry about this is because I'm thinking about particle wetting. I have a particle surrounded by air, and then if I put it into a liquid, am I going to have a large contact angle and kind of these beads of liquid forming with a little air in between? Or is liquid going to spread across the particle? Now, of course, I want that small contact angle and good wetting, because the goal is really to completely coat the particle with liquid and not have any air and not have any other particles sticking to it instead. It just wants to love that liquid. So there is a way to screen for good wetting agents, and this is handy if you don't really know what to use, if something's really giving you trouble, which is you can set up vials or beakers with each can of dispersant. So I might have one vial of alcohol, one vial of pure water, one vial of 0.1% tetrasodium pyrophosphate, one vial with 0.1% IGPAL. And then I'm going to put a little bit of the fine particles on the top of each liquid. So now we're going to zoom in, and if you look at the picture on the left, you can see that those little bitty particles are just sitting on top. They don't break through the surface tension of the water, okay? That means we have really a poor wetting. And if you have good wetting, the particles just separate and stream through the surface. And it's kind of hard to see on the right, but they're just little teeny particles kind of flying down the liquid. So one caution with this technique is if you put on a big clump of particles from a high height, gravity takes over and pulls it down through the surface tension. So you really want to kind of gently put it on there, so surface tension effects are important. And so you can look at these and say, well, if these four, the alcohol worked, then maybe the sodium pyrophosphate showed good wetting. But let's try the sodium pyrophosphate because it's easier to handle than lots of alcohol. Now, as I add surfactant, you're going to find out that if you measure mean particle size as a function of surfactant concentration, and the sample is not too well behaved, and look, you wouldn't be doing this if it was well behaved, you're going to see a minimum measured size with surfactant concentration. And that can be a fairly shallow effect. So as you add initial surfactant, the particle size goes down because you're just coating surfactant onto the surface of the particle. And then when you get to too much, you're going to see that you're forming micelles, and that will actually pull surfactant away from the particles. So common concentrations are 0.01 to 0.1 weight percent surfactant in water. So the mechanism for surfactants, of course, is that you have, say, a nonpolar hydrocarbon as a stick and a polar head, which could be ionic dipole, or it could be just a polar compound or polar group. And this is in a nonpolar solvent, and so the polar heads stick to the particles, and nonpolar hydrocarbon is sticking out, and that makes the solvent like that surface because it sees the nonpolar hydrocarbons, and so it surrounds the particle and separates the particles. So what happens as you add more surfactant? Well, so what happens is that you go up above the critical micelle concentration, and you'll see that the surfactant molecules tend to clump up and form their own micelles, which are kind of basically particles. And what that means is that surfactant molecules used to have two choices: be alone in the liquid or be on the particle surface. And they tended to like the particle surface because it would be polar in this case. Now they have a third choice. They could be with their friends, which are also polar. And so really what this means is when you get above the critical micelle concentration, you're going to start giving the surfactant molecules a friendly place to go besides the particle surface, decreasing the effectiveness of the surfactant. So basically, as you drive your surfactant concentration too high, you decrease the effectiveness of the surfactant. So there is a real maximum. And surfactants are expensive, so it's always good to use a little less material. Okay, now what is the effect of surfactant addition? This is kind of the whole thing rephrased. No surfactant, I have agglomerated particles. Optimal concentration, I have proper dispersion. And with excess surfactant, I have re-agglomeration of the particles because the surfactant is going out into the liquid. Here are some common surfactants: IDPAL CA630, Triton X, Tween, aerosol OT. Most of these are non-ionic and create steric barriers. Use ionic surfactants to form charged particles. Cationic surfactants, which I don't mention here or list, are often used for biological samples. If you're working in an area with a lot of activity or even modest amounts of activity, you can start looking online and using Google to see what surfactant packages or what surfactant approaches other people use in their method development. So you might Google something like TiO2 laser diffraction and then look at the methods in any papers that you find. Moving on to some smaller molecules, sodium hexametaphosphate and TSPP, tetrasodium pyrophosphate, are two crowd favorites, tend to work well with oxides. Again, you're dispersing at 0.01 to 1 weight percent. And so really you're putting a sample into this surfactant and then dispersing it and then making your measurement. I've seen labs where they just have 5 or 10 gallons of surfactant solution and they do their entire measurement in surfactant solution. They don't try and dilute after they've dispersed the particles in a concentrated solution. So that approach may work for you as well. Kind of worth talking a little bit about particle interactions. This really gives you some ways to think about what's happening in your system. So particles are constantly moving around with respect to each other due to thermal energy and also due to just flow within a container. But when they get close enough to cross kind of a potential barrier, then they come together and agglomerate. And really the name of the game is I want to keep the particles far enough away that they don't touch. And once they touch, they say, hey, my surface area is lower, so I have lower energies touching. Okay. And so we accomplish this with surfactants. Kind of another way of phrasing this is that van der Waals forces, which is what sticks things together, tend to be pretty weak over long distances. As you get closer, you have more and more van der Waals attraction, and we can use electrostatics to push them away. This invariably leads to the classic graph of potential energy as a function of distance between the surfaces. And you have a repulsive term due to electrostatics and an attractive term due to van der Waals interactions. And you'll sum them to get the net interaction. And you're really trying to ensure that the distance never gets past this peak where decreasing potential energy brings them closer and closer together. There are two ways to do this. The first is what's called steric stabilization, where we're going to use basically a polymer brush to keep the particles apart. So you'll have just kind of long, hairy chains sticking out from each particle, and that keeps them far enough away that they never really get close enough to attract each other. Or you could charge the particles up. Charging the particles up brings into the concept of Zeta Potential. And the Zeta Potential is the surface charge at the shear plane. So if you have a particle and it's charged, you'll have kind of a Stern layer of counter ions attached to it. so the charge potential will go down somewhat. And then you'll have the particle and those things moving around, and the rest of the liquid is an approximation. And that plane between the particle and what moves with it and the rest of the liquid, you find the charge, and that is the Zeta potential. It's a very useful concept when you're thinking about electrostatic stabilization. And people in formulation will often measure it to decide which formulation strategies make the most sense to really see which sets of particles are most highly charged and least likely to agglomerate and either cream or settle. Okay, so we've kind of described everything that happens on a particle surface, a couple different ways to look at it. So how do we get these particles separated to get those surfaces? And you want to push the particle. If the particles are touching, you're not going to get any surfactant between them. So you need to push them apart. And the way you'll do that is you're going to use energy, either a blender or a stirrer or ultrasonic devices, ultrasonic bath or ultrasonic probe. So you might take your particles, you put it into a surfactant solution, and then as you add energy, the surfactant kind of gets between the particles as they're jostled apart, and that keeps them apart. And so that's would be a kind of an overall strategy. Ultrasound is very popular. We have an onboard ultrasound in our analyzers, and ultrasonic waves generate microscopic bubbles or cavities or shear, which produces shearing action, and that forces the particles apart. You break apart agglomerates. Sometimes you can shatter fragile particles. And so the choice of energy has to be made somewhat carefully. So ultrasonic baths are fairly common at lower power. You can get ultrasonic probes that dump so much energy into a sample that you put your sample on ice to keep it from heating up too much. So ideally, you have a plot like the one here, where I have aggregate size on the left as a function of increasing energy, and the size is going down as I increase energy. And then there's a flat spot where I've broken the agglomerates, and then it starts going down again as I add more energy and start milling the particles. And that's great, but it doesn't always happen. So ideally, I'm saying I have aggregates on the left. I add the proper air pressure, which is another way of adding energy, particularly for a dry system. I break up the particles, break up my agglomerates to get something I can measure. And if my air pressure goes much higher, I'll break the particles into little bitty new particles and mill them. In the real world, you're going to add air pressure, you're going to break up your agglomerates, and you're also going to kind of might break up one or two particles as well. And so you really, instead of having that sharp transition I showed you at a very flat spot, you're going to have it much softer. And then when the air pressure gets too high, you are into milling. So this is a comment to say that when you look at this plot or these kind of thoughts of, oh, what's the optimum range, you can find out that, hey, you know what? This softens out a lot more than you really want to. It's not as obvious. And you'll start looking for things like what gives me the most repeatable result, because that is also important. So kind of in summary, surfactants will enable powders to be wetted. Use some sort of additive to alter your surface chemistry of your particles, sodium hexametaphosphate, sodium pyrophosphate, and the other ones are listed. Ultrasound or air pressure can reduce particle size by adding energy, and that can either be deagglomeration, which is good for the purpose of this talk, or breakage, which is bad for this purpose of this talk. Because remember, we're analyzing the particles, we're not trying to mill them or modify them. That may be a different process step. All right, well, that about covers everything. So I want to say thank you and open the virtual floor for questions. So someone says, is it possible to determine CMC with Zeta Potential? I've not seen it done with Zeta Potential. Generally, I've seen CMC determined by looking at scattered intensity or particle size as a function of surfactant concentration. So if you imagine you go into your analyzer and you try to measure particle size, with almost no surfactant, if you either measure the size of the individual molecules, if you're doing dynamic light scattering, or you won't see anything because there's no particles. Then as you start increasing your surfactant concentration, you'll see that the measured size jump up, and that will tell you, okay, this is the concentration where I'm forming my cells, because now I have big micelles compared to tiny little particles or tiny little molecules. The other option with some analyzers is you can look at the scattered intensity as a function of surfactant concentration, and it will increase linearly, and they will jump up dramatically when at the CMC. So those are two approaches. All right, next one. Actually, there are two that are related, so I'm going to mention. So the first is, should I use a dispersant to measure sand? And the second is when to use dry analysis versus wet analysis for a powder. And okay, so they're related because when you think about sand, the first thing is that if you take beach sand, and I'm not sure about other formations of sand, but if you take sand from the beach, there's a fair amount of organic matter, and that makes it sticky. And a lot of people will wash the sand before analysis. And most of what I've seen people do is wash the sand, dry it, and then analyze dry. Okay, so that kind of answers dry versus wet. In this case, it is dry. So sand is big, not much surface area, so it tends not to have a lot of issues with dispersion. It's really going to be down to sampling issues. So no dispersion on sand, but make sure it's clean and not sticky. And I run sand dry because it's already dry, and why mess around with water? And that comes down to dry versus wet. If the particle sample is dry and you can run it dry, it's easier. So you do that. As you get to smaller particle sizes, you'll often need liquid to mediate the interactions between the particles, and you have a lot more choices than just air. So you're going to start thinking about water, start thinking about surfactants for wet analysis. So it depends. All right, next question. How do you differentiate micelles from sample particles? Well, if your micelles are about the same size as your particles, you can't. So, and I've seen samples where it looks very much like I'm looking at some micelles and some analyte particles. What you can do is you can analyze just your surfactant package and see what particles you measure. And you find out that you have 100 nanometer particles from your surfactants as micelles, and you're trying to measure 100 nanometer particles of protein aggregate, for example, you're in trouble. So you might start thinking about what you can do to label the more interesting part of your sample, or what you can do to cut down your surfactant concentration. Best range of ultrasound for silica for TM50. TM50, if it's Ludox, if you get fresh Ludox, which means you haven't left it in the lab to crystallize for 2 weeks like I have, you don't really do much of anything to further dilute it. So quite often you can take TM50, and at TM50 I will, for particle size, I'll be using dynamic light scattering, and I will dilute it in salt water and then make my measurement. Away you go. You just need some gentle stirring. And that's because they charge the bejesus out of it. So it's a very highly charged particles. Okay, and with that, I'll say thank you very much to everybody. You can reach out to us at labinfo@horiba.com. And bye for now.